There is a piece of land in northern Canada where the ground moves, not because of an earthquake, not because of a flood. It moves on its own, slowly, in the way that something alive moves when it is breathing. The soil rises in the summer and sinks in the winter. Long ridges push up out of flat plains without explanation. Perfectly circular lakes appear in places where there were no lakes the year before. Trees tilt at strange angles because the earth beneath their roots has shifted in the night. Cracks open in the ground that are deep enough to swallow a person, and then close again by spring. Scientists have been studying this for decades. They have names for all of it. They have papers and measurements and models and funding proposals. They argue about mechanisms and rates and tipping points. Some of them have spent their entire careers trying to understand why certain parts of the Canadian landscape behave the way they do, as though the land itself has a schedule, a memory, a set of instructions it is following that nobody gave it. But here is what almost none of those papers mention. The people who have lived on this land for 10,000 years already knew. They knew the ground moved. They knew certain places were dangerous. They knew that beneath the surface of the earth there were forces that could swallow a village, poison a water source, collapse a hillside, or release something into the air that killed animals and made people sick. They passed this knowledge down through oral tradition, through ceremony, through the careful instruction of children, through land use patterns that archaeologists are only now beginning to understand. And here is the part that should stop you. The warnings were specific. They were not vague spiritual cautions about respecting nature in a general sense. They were precise. This hill, do not dig here. This valley, do not build a permanent structure. This lake, do not drink from it after a hard rain. This stretch of flat ground that looks solid, it is not solid. These warnings were given to the same places, by different First Nations groups who had no contact with each other, across distances of thousands of kilometers, and they match the geological record with an accuracy that has made more than a few scientists sit very quietly for a long time. This is the story of what they knew, and when they knew it, and what we are only now beginning to understand about why. Canada is the second largest country on Earth. Most of it is empty by the standards of modern settlement. The boreal forest alone covers nearly 600 million hectares. The permafrost zone extends across 60% of the country's landmass. There are river systems in northern Ontario that have never been mapped by a Canadian government agency. There are lake districts in the Northwest Territories that no non-Indigenous person has ever walked through. There are areas of the Canadian Shield, that vast ancient slab of Precambrian rock that forms the geological backbone of the continent, where the rock is so old it was already ancient when the first multicelled organisms appeared on Earth. Into this landscape, about 15,000 years ago, the first people arrived. They came from Beringia, the land bridge that connected Asia and North America during the last ice age, when sea levels were low enough to expose a corridor of land between what is now Siberia and Alaska. They came in groups over generations, following animals and coastlines and river systems southward and eastward into a continent that no human being had ever touched. They were not a single people. They were dozens, eventually hundreds, of distinct cultures, with different languages, different technologies, different cosmologies, different ways of understanding the world. But they shared one thing: they paid attention. For 10,000 years, they paid the kind of attention to the land that only comes from complete dependence on it. They did not have the option of not paying attention. The people who misread the landscape died. The people who understood it survived and had children, and taught those children everything they had learned, and those children taught their children, and the knowledge accumulated across generations in the way that only oral tradition can accumulate it, dense and layered and precisely calibrated to the specific conditions of specific places. What follows is a record of what they warned us about, and what the ground beneath Canada is, finally, after all this time, telling us about why they were right. Number 1, the Dene people and the trembling ground. The Dene are one of the most widely distributed indigenous peoples in North America. Their traditional territory spans an enormous arc across what is now northern Canada, from the Northwest Territories east into Nunavut, south into British Columbia and Alberta, and into parts of Saskatchewan and Manitoba. Different Dene-speaking groups have distinct names and distinct traditions, but across this vast territory they share a related family of languages, and more relevantly, here, a related body of knowledge about the land beneath their feet. The Dene have a word that translates roughly as trembling ground. It refers to a specific type of terrain that looks solid from a distance but behaves unpredictably when you walk on it. The traditional instruction associated with trembling ground was consistent across Dene-speaking communities that had no direct contact with each other. Do not build on it, do not dig into it, do not trust it after the warm season, and do not bring your animals onto it after heavy rain. For most of the 20th century, when non-Indigenous settlers and government agencies were drawing maps and planning infrastructure in the north, this knowledge was not consulted. It was, in the language of colonial administration, folklore. It was the kind of thing that went into ethnographic reports, filed in archives, and then left there. Then the permafrost started collapsing. Permafrost is ground that has been continuously frozen for at least 2 years, and in most of the Canadian North, it has been continuously frozen for thousands of years. It underlies approximately half of Canada's landmass. When it freezes, it is hard. When it thaws, either because of natural warming cycles or because of the accelerated warming that has characterized the last 50 years, it becomes something else entirely. The technical term is thermokarst. The practical reality is that solid-looking ground turns into a slurry of saturated soil, ice, and organic matter. Hills collapse. Flat land develops craters. Roads buckle. Buildings tilt and sink. Entire hillsides slide into rivers. The Dene elders who described trembling ground to anthropologists in the mid-20th century were not describing a spiritual concept. They were describing thermokarst terrain, and they were describing it with a precision that could only come from 10,000 years of direct observation. They knew which hillsides would fail. They knew which flat sections of seemingly stable ground were underlain by massive ice lenses that would melt in a warm summer and leave a sinkhole large enough to park a bus in. They knew the warning signs, the way certain grasses grew in patterns that indicated ice-rich soil beneath, the way the ground made a particular sound when struck with a stick in the right season, the way water pooled in places it should not pool. In 2010, a team of researchers at the University of Ottawa began cross-referencing Dene traditional land use patterns, compiled from historical ethnographic records, with modern permafrost mapping data. The correlation they found was startling. The areas that Dene communities had consistently avoided for permanent settlement matched the areas that modern geological surveys had identified as highest risk thermokarst zones with a precision that could not be explained by coincidence. In some cases, the specific hills and valleys that Dene oral tradition identified as unstable corresponded to geological features that had only been identified through satellite imaging in the 21st century. The trembling ground was real. The Dene had known about it for longer than written history. And in a period of accelerating permafrost collapse, when Canadian infrastructure is failing across the north at a rate that engineers did not predict and cannot fully explain, that knowledge is not folklore. It is the most accurate geological survey ever conducted in the country. Number 2, the Cree, warning about the hollow places. The Cree are the largest group of First Nations in Canada. Their traditional territory spans an immense stretch of the country's interior, from the Rocky Mountains in the west to Labrador in the east, taking in most of the boreal forest belt across what is now Alberta, Saskatchewan, Manitoba, Ontario, and Quebec. Within this territory, different Cree-speaking communities develop their own specific bodies of local knowledge, but certain themes appear consistently across the whole of Cree tradition. One of the most persistent is the concept of hollow places. The Cree term, rendered in different ways by different communities, refers to ground that sounds different when you walk on it or strike it, ground that is hollow below the surface, ground through which water moves in ways that are not visible from above, ground where the earth can open without warning. The instruction that accompanied this knowledge was precise. Do not make your permanent camps on hollow ground. You can travel through it. You can use it in the short term. But do not anchor your life to it, because it will not hold. For a long time, this was understood by outside observers as a generalized caution, perhaps related to the dangers of crossing frozen rivers or walking on thin ice. But the hollow places the Cree described were not bodies of water. They were solid ground, or ground that appeared solid. Beneath a substantial portion of the Canadian Shield and the interior plains, there are caves. Not the well-known tourist-friendly caves of the Rocky Mountains, though those exist too, but a vast and largely unmapped network of underground dissolution features, places where acidic groundwater has slowly dissolved the underlying limestone, dolomite, or gypsum over thousands of years, leaving voids of varying sizes at varying depths. Some of these voids are large enough to constitute cave systems. Some are smaller, irregular hollows that hold no particular drama in themselves, but are distributed across wide areas in patterns that are difficult to predict from the surface. When the ceiling of one of these voids becomes too thin to support the weight of what is above it, it collapses. The result is a sinkhole. Canada has sinkholes. It has sinkholes that appear overnight, that are tens of meters deep, that swallow roads and agricultural land, and in several documented cases, buildings that were constructed without anyone knowing what was beneath them. In 2013, a significant sinkhole opened in a residential neighborhood in Ottawa, the country's capital. It was 20 meters deep and roughly the size of a large house. In 2015, a stretch of highway in Alberta that had been used without incident for decades developed a collapse feature that shut the road for months. In 2019, a series of sinkholes appeared in an area of northern Manitoba that had been identified as geologically stable on every survey conducted in the preceding century. None of these collapses occurred in areas where Cree traditional knowledge indicated permanent settlement. All of them occurred in areas that, for reasons that are easy to attribute to coincidence and very difficult to attribute entirely to coincidence, were used by Cree communities only as travel corridors and seasonal hunting grounds, never as the sites of permanent villages. The hollow places. When geologists began in the early 2000s to systematically survey karst topography in Canadian interior regions, they found something that complicated their models. The distribution of karst features, the dissolution cavities, and the collapsed sinkholes and the areas of subsurface void space did not follow a simple geological pattern. It was irregular, patchy, influenced by a complex interaction of rock type, groundwater chemistry, depth of cover, and glacial history. Predicting where the ground was hollow from the surface using standard geological techniques was genuinely difficult. The error rates in karst hazard assessments were significant. Engineers building on apparently stable ground found subsidence and collapse at rates that their surveys had not predicted. But the Cree, had managed it. For 10,000 years, with nothing but observation and accumulated knowledge, they had mapped the hollow places well enough to orient their entire settlement pattern around, avoiding them. Not perfectly, not with zero risk, but with a consistency and accuracy that the most sophisticated modern survey techniques have only begun to approach. Number 3, the Anishinabe and the breathing earth. The Anishinabe peoples, who include the Ojibwe, Ottawa, Potawatomi, Algonquin, Saulteaux, Mississauga, and several other related groups, traditionally occupied a vast territory around the Great Lakes and extending north and west into the boreal forest. Their oral tradition is among the most extensively documented of any North American indigenous group, partly because of the early contact they had with Jesuit missionaries and French explorers who wrote detailed accounts of what they were told, and partly because of the extraordinary efforts of Anishinaabe scholars and knowledge keepers in the 20th and 21st centuries to record and transmit what might otherwise have been lost. The Anishinaabe concept of the breathing earth is not a metaphor, or rather, it is not only a metaphor. When Anishinaabe elders spoke of the earth breathing, they were partly speaking in the symbolic language of a cosmology that understands the natural world as alive in ways that Western science does not recognize. But they were also describing something observable, something physical, something that if you spent enough time in the right places, you could actually see. The earth breathes, particularly in areas of high organic content, in wetlands and bogs, and the thick forest floor of the boreal zone. The ground does something that looks, if you are paying attention, very much like breathing. It rises and falls, not in a human respiratory rhythm, on a time scale of seasons and years rather than seconds. But the movement is real, and it is measurable, and it is caused by something that modern geochemists now understand quite precisely: methane. Beneath the wetlands, bogs, and lake sediments of the Canadian boreal zone, enormous quantities of organic matter have been accumulating for thousands of years. Peat bogs in Canada store more carbon than all of the country's forests combined. As this organic matter decomposes under waterlogged, low oxygen conditions, it produces methane. The methane accumulates beneath the surface. It gets trapped under ice in winter, builds pressure, and releases in spring and summer, sometimes gradually, sometimes suddenly, in bursts that make the ground look like it is breathing. In recent years, scientists studying methane emissions from Arctic and subarctic Canada have been alarmed by what they are finding. The warming of the permafrost zone is causing the release of methane at rates that were not predicted by any model built in the 20th century. The gas is seeping from the ground, bubbling through lakes, venting from hillside seeps, emerging from cracks in the frozen earth that were not there 5 years ago. In some areas of the Northwest Territories and northern Quebec, the methane release is visible. You can see it. The ground is, in a very literal sense, exhaling. The Anishinaabe oral tradition contains multiple accounts of places where the earth breathed strangely, places where the air near the ground smelled different, where animals avoided certain areas, even in good weather, where fires started without obvious cause and burned underground for seasons at a time. The instruction associated with these places was consistent. The earth is not done there. It is still making something. Do not interfere with it. What it was making, in the language of modern geochemistry, was methane and carbon dioxide, in concentrations that could be dangerous to breathe in enclosed spaces, that could ignite, and that, in the case of sudden large releases, could displace the oxygen in a low-lying area fast enough to suffocate a person or an animal before they understood what was happening. There are documented cases in modern times of farmers in parts of Ontario and Quebec dying in farm pits and unventilated basements from methane and carbon dioxide accumulation. There are documented cases of livestock dying in areas where the soil gas composition was anomalous. These deaths are reported as accidents, as unfortunate encounters with a hazard that was not recognized. They happened in places where, if anyone had consulted the Anishinabe knowledge of that land, the hazard would have been identified immediately. The breathing earth. Number 4. The Blackfoot Confederation's sacred avoidance. The Blackfoot Confederation, comprising the Siksika, Kainai, and Piikani nations on the Canadian side of the border and the Blackfeet Nation in Montana, occupied the northwestern Great Plains and the foothills of the Rocky Mountains. Their traditional territory was a landscape of extraordinary drama, one of the most seismically and geologically active regions of the continent. The Rocky Mountain foothills are not stable ground. They never have been. The geology of this region is the result of one of the most violent tectonic events in North American history, the Laramide orogeny, a period of mountain building that lasted from roughly 80 million to 55 million years ago, and that left the landscape in a state of permanent slow-motion adjustment. The mountains are still rising and falling, in increments invisible to human perception but measurable by modern instruments. The foothills are cracked through with fault lines, some of them active in a seismological sense, many of them active in a more subtle sense, conducting groundwater and gas and heat from deep in the earth to the surface in ways that make certain areas behave very differently from the ground around them. The Blackfoot Confederation had a category of sacred avoidance for specific locations within their territory. These were places that were acknowledged to exist, that were known to the community, that were even approached in ceremonial contexts, but where permanent occupation was explicitly and consistently prohibited. The reasons given in oral tradition were various. The land there was spoken for by forces that humans should not disturb. Certain animals avoided those places, and therefore humans should too. The water there tasted different, and was not safe for sustained use. The ground made sounds in the night that indicated something active below. These are not vague prohibitions. The Blackfoot descriptions of sacred avoidance locations correspond with remarkable specificity to what geologists now call fault zone expressions, places where the geology of the underlying bedrock is expressed at the surface in ways that create unusual and sometimes hazardous conditions. Gas seeps, saline springs, areas of anomalous soil temperature, places where the rock is fractured and the ground subsides unpredictably, places where earthquakes, when they occur, cause surface deformation rather than simply shaking, because the faults are shallow and the damage is done close to the surface where people live. One of the most instructive examples involves the area around what is now the city of Lethbridge in southern Alberta. The Oldman River Valley in this region is underlain by a complex geology that includes natural gas deposits, coal seams, and a system of faults that has produced several significant earthquakes in recorded history. The Blackfoot knew this valley well. They camped in it, hunted in it, used it extensively. But the specific sections of the valley where the underlying geology was most disturbed were areas where traditional knowledge indicated seasonal use only, and where the construction of permanent structures was against the traditional understanding of the land. When coal mining began in this region in the late 19th century, the miners encountered conditions that match what Blackfoot knowledge had suggested about those specific areas. Unexpected gas pockets, unstable ground, water infiltration from sources that the surface geology did not predict. These were not surprises in a geological sense. They were the surface expression of exactly the conditions that traditional knowledge had been tracking for thousands of years. The Blackfoot were not geologists in the Western academic sense. They were something more practical. They were people who had been running a 10,000-year field study on the behavior of specific pieces of ground, and they had drawn accurate conclusions from what they observed. Number 5. The Haida and the sunken coastlines. Haida Gwaii is an archipelago off the northern coast of British Columbia, a chain of islands that have been called the Galapagos of the North for their extraordinary biodiversity and ecological distinctiveness. The Haida people have lived on these islands for at least 14,000 years, which means they were there before the end of the last ice age, and they were there when the sea levels were different, when the coastline was different, when the relationship between land and water in this part of the world was fundamentally unlike anything visible on a contemporary map. The oral tradition of the Haida contains detailed accounts of lands that are no longer above water, villages that are now beneath the sea, coastlines that existed before the great changes, before the time when the ocean came up and swallowed the lower ground. These accounts were understood by most outside observers who encountered them in the 19th and early 20th centuries as mythology, as symbolic stories about transformation and loss, perhaps about floods in the religious sense. They were filed alongside other creation narratives and treated accordingly. Then marine archaeologists began exploring the submerged continental shelf around Haida Gwaii, and they found things: stone tools, middens, the accumulated refuse of human occupation, shell and bone and charcoal preserved beneath the sediment of the sea floor, evidence of human habitation in places that have been underwater for 9,000 years. The Haida oral tradition was describing real places, real villages, a real coastline that existed, that was inhabited, and that was then inundated as the glaciers of the last ice age melted and sea levels rose in the period that geologists call the Holocene transgression. But the Haida knowledge goes beyond the historical record of what was lost. It extends forward into an understanding of what was still happening, what the land was still doing, what the sea was still capable of. The oral tradition of the Haida includes specific warnings about coastal areas that are subject to sudden submergence, places where the ground drops away without warning, where earthquake-related tsunamis and landslides into the sea can generate waves that reach far inland. Haida Gwaii sits directly over the Cascadia subduction zone, one of the most seismically dangerous fault systems in the world. The last major rupture of the Cascadia fault, estimated to have been a magnitude 9 or greater earthquake, occurred in January 1700. The Haida oral tradition contains an account of this event, a description of the shaking and the wave that followed, told from the perspective of people who survived it by understanding that when the earth shook in a specific way, you moved immediately to high ground and you did not return to the coast until the water had come and gone. This is not generalized earthquake preparedness. This is specific knowledge of a specific type of seismic event and the specific response that maximizes survival. The Cascadia subduction zone is overdue for another major rupture. When it comes, it will affect the entire Pacific coast of Canada from northern British Columbia to Vancouver Island. The communities that survive best will be the ones that understand the warning signs and respond immediately with the behaviors that traditional Haida knowledge has encoded for millennia. Move to high ground, stay there, wait. Underground, in this case, means something specific. It means the place where the Juan de Fuca tectonic plate is sliding beneath the North American plate at a depth of roughly 30 kilometers, accumulating strain that will eventually release in a fraction of a second and ring the entire Pacific Rim like a bell. The Haida did not know the plate tectonic mechanism. They did not need to. They knew the outcome, and they knew the warning signs, and they built that knowledge into the instructions that every generation received about how to live on this particular piece of the earth. Number 6. The Inuit knowledge of moving ground. The Inuit occupy the northernmost reaches of Canada, the Arctic and subarctic zones above the tree line, a landscape so extreme that no other people on Earth had figured out how to live there permanently. That the Inuit did and do is one of the most remarkable achievements in human history, and it required a quality of environmental observation that is without parallel in any other cultural tradition. The Arctic is a landscape that is substantially underground in a meaningful sense. The permafrost in the Canadian Arctic extends to depths of hundreds of meters in some areas. The surface layer, what is called the active layer, freezes and thaws seasonally, but below it the ground is permanently frozen, and has been permanently frozen for so long, in some places, that it contains ice from the Pleistocene epoch, 2 million years old. The relationship between what is visible on the surface and what is happening underground is the fundamental defining feature of the Arctic environment. The Inuit developed a vocabulary for ground conditions that has no equivalent in any European language, because European languages were not developed in this environment and had no need for this level of specificity. There are Inuit terms for different types of ice formation within the ground, for the way certain soils behave when the ice within them melts, for the difference between ground that is safe to walk on and ground that looks the same but is not. There are terms for the specific sound that different types of ground make when struck, which is useful information because you can hear things about what is underground that you cannot see. This vocabulary was functional. It was the difference between walking safely and breaking through into a void. It was the difference between building a structure that would remain standing and one that would lean and eventually collapse. It was the difference between digging a food cache that would remain cold and accessible and one that would be undermined by melt and lost. Every term in this vocabulary represented a specific hazard that had been identified, named, and incorporated into the practical knowledge of how to survive in this place. The Inuit knowledge of moving ground has become urgently relevant. The Arctic is warming at a rate 2 to 3 times faster than the global average. The permafrost is thawing at depths and in areas that the most pessimistic climate models of the 20th century did not predict. The active layer is deepening. The ground ice is melting. The landscape is changing in ways that are visible to the naked eye within single human lifetimes, which was not true for any period of Inuit occupation before the last few decades. In community after community across the Canadian Arctic, Inuit elders are describing changes to the landscape that alarm them. Coastal bluffs that are eroding at rates they have never seen, flat areas where ponds are appearing that have no historical precedent, hillsides that are slumping and revealing the ice-rich material within them, coastlines that are changing year by year in ways that traditional knowledge does not have terms for, because the traditional knowledge was built on a landscape that was stable on a timescale of thousands of years, and what is happening now is something different. The warning has inverted. For 10,000 years, the Inuit knowledge of moving ground was a warning about what the ground could do to the unwary. Now it has become something else. Now the Inuit are the ones issuing the warning, telling the outside world what they can see happening to the ground beneath their feet, and what it implies for what is happening underground on a scale that extends far beyond the Arctic. The permafrost in the Canadian North contains more stored carbon than the entire atmosphere currently holds. When it thaws, it releases that carbon. The ground is not just moving, it is opening, and what is coming out of it is going to change the air of the entire planet. Number 7, the methane mystery when the ground starts bubbling. In 2011, a scientist named Katie, Walter Anthony, published photographs of a lake in the Siberian Arctic in which bubbles of methane gas were rising through the water and freezing into the ice on the surface. The photographs were striking. The lake looked like it was alive, like something enormous was breathing beneath it, like the bottom of the lake was slowly exhaling. The photographs were widely circulated. They became a kind of emblem for the thawing permafrost problem. What was less widely reported was that lakes that do this, lakes that bubble methane from sediments disturbed by warming and thaw, have been known to the indigenous peoples of the circumpolar north for as long as there has been knowledge of the north. The Cree in Canada, the Dene in the Northwest Territories, the Inuit in the Arctic, all had knowledge of lakes and wetland areas where the water bubbled, where the gas that came up from the bottom could be lit with a flame and would burn, where the smell of the water near the shore was different in ways that indicated something active beneath the surface. The Gwich'in people of the Mackenzie Delta region in the Northwest Territories have oral tradition accounts of specific lakes, where the bubbling was so vigorous that the water appeared to be boiling in cold temperatures, and where the gas that accumulated at the surface could be ignited. This was not mysterious to them. It was simply a characteristic of those specific lakes, a characteristic that had been documented across generations, and that was encoded in land use knowledge. These lakes had resources, you could fish them, but you treated them carefully. You did not make open fire too close to the shore in calm conditions. You understood that the water was participating in a process you should not interfere with. The methane in these lakes comes from the same source as all permafrost methane, the decomposition of organic material that was frozen tens of thousands of years ago and is now, as the permafrost thaws, being exposed to microbial activity that breaks it down and produces gas. The lakes are particularly active because the warming water accelerates the process, and because the sediment disturbance created by thaw slumping at the lake margins introduces fresh organic material that feeds the decomposition cycle. What makes this particularly significant for understanding what First Nations knowledge was tracking is the geography of these lakes. They are not randomly distributed. They cluster in areas of specific permafrost type, specifically areas with high organic content and irregular ice distribution. They cluster in areas where the permafrost is in a transitional state, not deeply frozen stable permafrost, but permafrost that is close to the thermal boundary where thawing becomes possible. These are the same areas that traditional knowledge identified as places of active underground processes. The First Nations knowledge was not just identifying the visible symptom, the bubbling lake. It was tracking the underlying geological condition that produces the symptom, the presence of ice-rich, carbon-rich, thermally sensitive permafrost. And it was encoding that knowledge in land use instructions that, if followed, kept communities out of areas where the ground was most likely to behave unpredictably. There is a lake in the Northwest Territories called Asia Lake, identified in 2019 as one of the most methane-productive lakes in the Arctic, releasing quantities of the gas that had previously been thought impossible from a single water body. A research team from the University of Alaska was the first to publish measurements of its emissions. But the Gwich'in people, whose traditional territory includes this lake, knew it as a place of active underground process, a place that was treated with particular care in terms of where you camped and how you used the surrounding land, for longer than any written record exists. The science caught up to the knowledge. It always does. It just takes a very long time. Number 8. The Sinkhole country. Nobody mapped. In the spring of 2016, a farmer in the area of Estevan, Saskatchewan, woke up to find a hole in his field. Not a small hole, a roughly circular depression approximately 40 meters across and 8 meters deep that had not been there the previous evening. The soil around the edge was cracked and slumping inward. The bottom of the hole was wet. There was no obvious cause, no drought that could explain it, no mining in the immediate area, no pipes or buried infrastructure to blame. The geological survey that followed determined that the collapse was the result of dissolution subsidence. Beneath that part of Saskatchewan, there is a geological formation called the Williston Basin, which contains thick layers of evaporate rocks, primarily gypsum and halite, salt, that have been dissolving in groundwater for millions of years. The dissolution creates underground voids, and when those voids get large enough, the overlying material collapses into them. Saskatchewan has hundreds of these collapse features. Some are ancient, now expressed as the shallow circular lakes called prairie potholes, so numerous they make aerial photographs of the prairie look like they were made by buckshot. Some are more recent and some are active, opening without warning in agricultural land, along highways, and on the edges of towns and cities. The provincial government maintains a database of known karst features, but the database is incomplete because dissolution subsidence in this region is spatially irregular and difficult to predict in advance. Before Saskatchewan was Saskatchewan, it was Cree, Assiniboine, Sioux, and Nakota country. The oral traditions of these nations, as documented by ethnographers in the late 19th and early 20th centuries, contain consistent references to what translates as hollow land, specifically in the region of the Williston Basin and the areas of southern and central Saskatchewan underlain by evaporate geology. The instructions about hollow land were practical. Travel through it, use it seasonally, but do not build your long-term life on it, and if the land makes a sound it does not usually make, move away from that sound immediately. The correlation between the known distribution of dissolution karst in Saskatchewan and the areas traditionally used by Indigenous peoples only as seasonal or transit zones rather than permanent settlement sites was examined in a 2018 research paper published in the Canadian Journal of Earth Sciences. The authors were careful with their language, as academics tend to be when they are saying something that challenges established frameworks. But what they were saying was clear. The indigenous land use patterns in this region could not be fully explained by the distribution of game animals, water sources, or any other ecological variable that did not include knowledge of underground geological hazard, hollow land, sinkhole country, a landscape where the ground was beautiful and flat and apparently simple, and was in fact doing something complex and dangerous beneath the surface. The Cree knew it. The Assiniboine knew it. The farmers who arrived in the late 19th century did not know it. And the holes keep opening. Number 9. The seismic belt. The ancients refused to settle. Canada is not commonly thought of as an earthquake country. That distinction belongs in the popular imagination to California, Japan, Chile, Turkey. But Canada has earthquakes. It has earthquakes regularly in some areas. It has had catastrophic earthquakes within historical memory, and it exists in geological context that makes future catastrophic earthquakes not a matter of speculation, but a matter of timing. The most significant seismic zone in Canada is the Cascadia subduction zone off the Pacific coast, which we have already discussed in the context of the Haida, but there are others. The Saint. Lawrence River Valley in Quebec is one of the most seismically active regions in eastern North America. The Charlevoix region of Quebec, north of Quebec City along the St. Lawrence, has been hit by major earthquakes in 1663, 1791, 1860, and 1925. The 1663 earthquake was estimated to have been magnitude 7 or greater, and its effects included massive landslides, river diversions, and the temporary appearance of geothermal activity in areas where none had previously been observed. The Inuit people, whose traditional territory includes the Charlevoix region and the north shore of the St. Lawrence, had knowledge of this area as seismically active that is encoded in their oral tradition and their patterns of seasonal land use. Specific sections of the St. Lawrence North Shore were used for hunting and fishing. but avoided for permanent winter camps on the grounds that the land there was not stable and could not be trusted over long periods. Ethnographic records from Jesuit missionaries who traveled with Innu groups in the 17th century note, with puzzlement, the Innu practice of relocating away from certain riverbank locations in autumn, despite those locations being apparently ideal camping sites, rich in resources, and protected from wind. The missionaries attributed this to superstition or to unfathomable traditional practice. What the Innu were doing was avoiding the areas most susceptible to earthquake-triggered landslides. The Charlevoix seismic zone produces a specific type of ground failure called sensitive marine clay failure, in which the clay deposits laid down by an ancient post-glacial sea, the Champlain Sea, which filled the St. Lawrence Valley about 12,000 years ago when the land was still depressed by the weight of glaciers, liquefy when subjected to seismic shaking, and fail catastrophically, sometimes carrying enormous volumes of material into rivers and lakes within seconds. This is not a theoretical hazard. There are documented cases of Haida clay landslides in the St. Lawrence Valley in modern times. The 1908 Notre Dame de la Salette landslide that killed 33 people, the 1955 Sinkhole landslide, the 1971 Saint-Jean-Vianney landslide that destroyed part of a town and killed 31 people, the 2010 Saint-Jude landslide, each one in an area where the underlying geology would have been recognizable to any person who had spent generations learning to read the specific warning signs of sensitive clay terrain. The Innu were reading those signs. The missionary accounts that puzzle over their campsite selections, when read alongside the modern geological map of Haida clay distribution in the St. Lawrence Valley, reveal a pattern. The avoided locations correspond to the areas of deepest, most sensitive clay deposit, the areas most vulnerable to rapid failure in a seismic event. The preferred locations correspond to areas with thinner clay cover, better drained terrain, or bedrock exposures that would resist the type of failure that the sensitive clay was prone to. This was not abstract knowledge. It was earned across generations through observation of what happened to specific pieces of ground when the earth moved. Someone, at some point, had seen a clay bank fail, had seen what was there one moment, gone the next, had understood that this was a property of certain types of ground and not others, had taught that understanding to the next generation and the next in a chain of practical instruction that stretched back to the Holocene. Number 10. What the Beaver people called the underground fire. The Dene, known in earlier ethnographic literature as the Beaver people, are a Dene-speaking nation whose traditional territory occupies the Peace River country of what is now northeastern British Columbia and northwestern Alberta. They are one of the smaller First Nations in Canada by population, and their oral tradition is less widely known than that of the larger nations, but it contains some of the most precise and technically verifiable observations of underground geological phenomena found anywhere in Canadian Indigenous knowledge. The Dene have oral accounts of underground fire, not volcanic fire. Canada does not have active volcanoes in this part of the country, but something different, something that burned beneath the ground, that produced heat you could feel at the surface in certain locations, that released smoke or vapor from cracks in hillsides, and that in certain places had burned for so long and so continuously that the rock and soil above it had changed color and character, had been altered by sustained heat, in the way that only fire alters things. This is not mythology. It is an accurate description of coal seam fires. The Peace River country sits above one of the most extensive coal-bearing geological formations in Western Canada. The coal seams are close to the surface in many areas, exposed in riverbank cutaways and hillside outcrops. Coal that is exposed to air and water can spontaneously combust. Coal seam fires, once started, burn underground at temperatures high enough to fuse the surrounding rock and can continue burning for decades or centuries. The altered, hardened rock left by underground coal fires is called clinker, and the Peace River region has extensive clinker deposits that attest to a long history of underground burning. The Dene oral tradition does not treat the underground fires as inexplicable or supernatural. They are treated as characteristics of specific places, hazards to be navigated, features of the landscape that had practical implications for where you made camp, where you dug for water, and which hillsides you approached with caution. The accounts describe the way the ground above a burning seam was different, warmer than it should be, producing unusual vegetation patterns, occasionally releasing gas that smelled different from the surrounding air and that was dangerous in still conditions. This is precise hazard observation. Carbon monoxide and carbon dioxide emitted by underground coal fires in concentrations sufficient to be dangerous have killed people and animals in documented cases in many countries. The behavior of vegetation over underground fires, the differential growth patterns caused by elevated soil temperature and altered soil chemistry, is a real phenomenon that survives to modern times in areas where coal fires persist. The Dane observed these warning signs with enough accuracy to encode specific locational hazards into their traditional knowledge. When coal prospectors arrived in the Peace River country in the late 19th century, they were assisted in locating coal seams by the surface expressions of the geology, including some of the same clinker deposits that Dane tradition had been describing for generations. What the prospectors understood as evidence for coal deposits, the Dane had understood as evidence for underground fire. Different frameworks for the same physical reality. One of those frameworks was 200 years old when it arrived in the Peace River Valley. The other was at least 10,000 years old. Number 11, the permafrost collapse that scientists didn't predict. In 2017, a team of researchers flying over Banks Island in the Northwest Territories counted more than 60,000 permafrost thaw slumps on the island's surface. Retrogressive thaw slumps are a specific type of ground failure in which the melting of ice-rich permafrost causes the overlying material to fail and slide, creating a characteristic headwall scar that looks like a bite taken out of a hillside, and a debris lobe of saturated sediment. Extending downhill from the scar, Banks Island has always had some thaw slumps, but the 2017 count was not just higher than previous counts. It was an order of magnitude higher. The number of active slumps on the island had increased by more than 600% since the 1980s. No model built before 2010 predicted this rate of change. The failure was not primarily in the science of permafrost physics, which understood the mechanisms reasonably well. It was in the assumptions built into the models about how quickly and how extensively the warming would progress. The scientists were working with models calibrated to a rate of change that the real world was not following. The real world was moving faster. The Inuit of Banks Island had been telling researchers for years that the land was changing. Specific accounts, hillsides that were stable in their grandparents' time were failing. Coastlines that were solid when they were children were eroding. Lakes that had been there forever were draining, their bottom suddenly exposed as the permafrost beneath them collapsed. They described these changes with the specificity of people who had been reading that landscape for generations and knew exactly what normal looked like, and could therefore identify with precision what was different. These accounts were recorded by researchers. They were published. They were described as consistent with what the science was observing. But the quantitative models that inform policy, the models that governments use to plan infrastructure and climate adaptation were not updated to match what the Inuit were saying with the speed that the situation warranted, because the Inuit accounts were treated as qualitative, as contextual, as useful for framing questions, but not as primary data. This is the central epistemological problem of the relationship between Western science and Indigenous knowledge. Both are observational systems. Both generate knowledge through observation of the natural world, but only one of them is treated as generating data in the formal sense, and therefore only one of them is allowed to drive quantitative models. The result, in the specific case of Banks Island and thaw slumps and permafrost collapse timelines, was that the models were wrong and the Inuit knowledge was right, and the policy implications of being wrong were significant and are ongoing. The permafrost beneath Banks Island contains carbon. The permafrost beneath the entire Canadian Arctic contains carbon. When it thaws, the carbon enters the atmosphere. The rate at which it thaws determines how much of that carbon enters the atmosphere over the next century, and that number matters enormously for understanding where the global climate is going. If the Inuit observations of change rates had been incorporated into quantitative models a decade earlier than they were, the projections for this century would have been different, more alarming, closer to what is actually being measured now. Number 12, the sacred lakes that drain overnight. There are places in Canada where lakes disappear, not seasonally, not over years through evaporation or drainage, but suddenly in the span of hours. A lake that is full in the morning is empty by evening. The basin is still there. The water is gone. In some cases, the lake refills over subsequent months as the water table recovers. In some cases, the basin remains dry for years. This phenomenon is documented in scientific literature under the term karst lake drainage or Doline lake failure, and it is the result of the same dissolution processes that create sinkholes. When the underground void that has been supporting the floor of a lake collapses or opens a drainage connection to a lower level, the lake drains through the opening. The speed and completeness of the drainage depends on the size and character of the opening. In some cases, it is gradual. In some cases, it is not. The woodland Cree and the Ojai Cree peoples, whose territories include the karst lake country of northern Ontario and Manitoba, have oral tradition, accounts of lakes that drink the water, lakes with a hole in their bottom, lakes that are here and then gone, and then here again. These accounts were documented by anthropologists in the early 20th century with the same skeptical framing applied to much Indigenous oral tradition. Probably a metaphor, possibly an exaggerated account of a drought, perhaps a story that has accumulated symbolic meaning over time and should not be taken literally. In 2006, a lake in northern Ontario that had been present on topographic maps since at least the 1930s drained in a matter of days during late spring, leaving a bare basin. Provincial geologists investigated and confirmed a karst drainage event. The lake had lost its bottom through a solution feature in the underlying dolostone. The local Ojai Cree community noted, with careful understatement when interviewed by a local journalist, that this lake had been known in their oral tradition as one of the lakes with a hole in its bottom. The knowledge was there. It was in the oral tradition. It was available to anyone who thought to ask. The scientific investigation confirmed what the traditional knowledge had been saying for generations. And the lake, after a period of recovery, partially refilled over the following years as local groundwater recharged the basin, matching another detail in the oral tradition, that this particular lake was one of the kind that sometimes came back. The ability to identify a specific lake, not karst terrain, in general, but this specific lake, as prone to drainage events, and to encode that identification accurately enough that it survived in oral tradition. For long enough to still be present when a researcher came to investigate a drainage event in 2006 is an extraordinary demonstration of the precision and durability of traditional ecological knowledge. This is not general environmental awareness. This is a geologic observation about a specific place maintained with accuracy across an unknown number of generations. Number 13, the underground river systems beneath the prairies. The Canadian prairies look simple. That is part of their appeal and part of what makes them dangerous. The flat expanse of the interior plains, stretching from the foothills of the Rockies east to the edge of the Canadian Shield, appears to be straightforward terrain. Dry, open, navigable, predictable. The complexity is underground. Beneath the prairies, particularly in Saskatchewan and Manitoba, there is an extensive system of underground water movement. Some of it follows the dissolution features in the evaporate formations we have already discussed. Some of it follows ancient bedrock valleys carved by glacial meltwater. During the retreat of the Laurentide ice sheet, channels cut into the bedrock that are now filled with glacial sediments, but that still conduct water underground along their ancient courses. Some of it follows fracture systems in the underlying Precambrian basement rock. The entire underground hydrology of the prairies is complex, poorly mapped, and in some areas poorly understood, even by the water management agencies whose job it is to understand it. The Nakota, Assiniboine, and Dakota peoples whose traditional territories covered much of the prairie interior had knowledge of underground water that was encoded in their reading of the surface. They knew that certain depressions in the flatland, certain arrangements of vegetation, certain behaviors of surface water in spring indicated underground water movement beneath. They knew that water tasted differently in areas where it had traveled through different rock, and that some of that water was not safe to drink in ways that were not visible at the surface. They knew the locations of springs that emerged from the underground system at the surface, and they knew the patterns of those springs, which ones ran year-round and which ones were seasonal, which ones produced safe water and which ones were mineralized. This knowledge of underground hydrology was not abstract. It was the knowledge that allowed survival on a landscape where surface water was scarce and unpredictable. The prairies in summer are dry. The rivers are seasonal and variable. The lakes are often saline. Finding safe, reliable water on the prairies, without modern well drilling technology, required understanding where the underground water was and how to access it. The precision of this knowledge is attested in the records of the surveyors and explorers who traveled the prairies in the 19th century. Multiple accounts from the 1870s and 1880s note the specific hydrological knowledge demonstrated by indigenous guides, the ability to identify, in terrain that appeared featureless to trained European observers, the location of water sources, the quality of water at different locations, and the behavior of the underground system in different seasons. One survey account from 1874 describes an Assiniboine guide leading the party directly to a spring in terrain where the surveyors had estimated there would be no water for another 30 kilometers, and where the geology gave no surface indication of what was below. The underground river systems of the prairies are relevant to contemporary issues in ways that extend beyond the historical record. The aquifer systems beneath the prairies are the primary water source for much of Saskatchewan's agriculture. They are being drawn down faster than they are recharging in some areas. They are contaminated in places by agricultural runoff, by the byproducts of oil and gas extraction, by the dissolution of naturally occurring minerals in the evaporate formations. Understanding their distribution, their recharge rates, their vulnerability to contamination is an urgent practical problem for which modern hydrogeology is the primary tool. But the traditional knowledge of underground water distribution in this region is, in principle, an additional dataset, a dataset compiled over thousands of years by people whose lives depended on its accuracy. The project of incorporating that dataset into contemporary water management has barely begun. Number 14. The Radon Zones and the Forbidden Hills. Radon is a radioactive gas. It is produced by the decay of uranium and radium, which occur naturally in certain rock types, particularly granitic rocks of the type that form much of the Canadian Shield. Radon seeps from the rock and soil, accumulates in enclosed spaces, and when inhaled over extended periods causes lung cancer. It is, after cigarette smoking, the leading cause of lung cancer in Canada. It is invisible. It is odorless. It is tasteless. There is no way to detect its presence without instrumentation. And yet, the granite and granodiorite rocks of the Canadian Shield have been known, in various First Nations traditions, as areas requiring specific behaviors in terms of where you built your shelters and how you ventilated them. The Anishinabe oral tradition contains accounts of places where the rock was warm in certain conditions, where spending extended time in enclosed spaces near the rock, in the caves and rock shelters that occur naturally in shield terrain, made people sick with a sickness that came slowly and affected the lungs. These accounts were so consistent across different communities within shield territory that they generated a general practice of preferring well-ventilated shelter designs and avoiding certain rock shelter locations for extended occupancy. The connection between uranium-bearing granite, radon emission, and lung disease was not made explicit in these oral traditions because the mechanism was not available as a concept. You cannot describe radioactive decay if you have no concept of radioactivity. But the outcome, the connection between specific places and a specific type of illness that affected the lungs and developed slowly, was observed and documented with enough consistency to influence behavior in the direction of risk reduction. This is perhaps the most remarkable of all the correspondences between traditional knowledge and modern science in this area, because radon hazard is genuinely invisible and genuinely counterintuitive. There is no way to identify high radon emitting rock by looking at it or by any observation that does not involve sophisticated measurement equipment. The only way to know that a particular type of rock emits radon at levels that are dangerous over extended exposure is to observe the health outcomes of people who spend extended time near it over a long enough period and with a large enough population to establish the pattern. That is exactly what a knowledge system that tracks health outcomes across thousands of years in a specific landscape can do. It cannot name the mechanism, but it can establish the correlation. These places, this type of rock, extended exposure, this type of illness, encode it in tradition, preferred ventilation practices, avoidance of specific shelter types in specific rock settings. Pass it down, not as a caution about radiation, but as a practical instruction about how to live in this specific environment in a way that maximizes long-term health. The Canadian Nuclear Safety Commission maps radon risk zones across Canada. The highest risk areas correspond, predictably, to uranium-bearing shield rock. When those risk zone maps are overlaid with historical Indigenous settlement patterns and shelter designs in shield territory, the pattern is consistent. The communities that spent the most time in the highest risk radon zones had adapted their shelter designs toward the configurations that modern radon mitigation science would recommend: elevated sleeping platforms, better ventilation, avoidance of enclosed ground-level spaces in high granite environments. They could not see the gas, but they could see the pattern of what it did over thousands of years, and they responded to it. Number 15, the Hudson Bay anomaly. There is something wrong with gravity over Hudson Bay. Not dramatically wrong, not wrong in the way that science fiction describes gravitational anomalies, but measurably, verifiably, persistently wrong. The gravitational field over and around Hudson Bay is weaker than it should be, based on the mass of the Earth's crust in that region. Instruments that measure gravitational acceleration show a consistent deficit, a low spot in the planet's gravitational field, centered roughly over Hudson Bay and extending outward into parts of northern Ontario, Quebec, and the adjacent ocean. Scientists have two explanations for this, and both of them are correct to different degrees. The first is that the Laurentide ice sheet, the enormous glacier that covered most of Canada until about 10,000 years ago, was so heavy that it depressed the underlying lithosphere, the solid outer layer of the Earth. When the ice melted, the lithosphere began to bounce back, but it has not finished bouncing back yet. The process of post-glacial rebound is ongoing. The land in and around Hudson Bay is still rising, in some areas at rates of more than 1 centimeter per year, as the lithosphere slowly recovers from being pressed down for tens of thousands of years under kilometers of ice. The incomplete rebound means that there is less mass in the crust of this region than there would otherwise be, because the lower density, hotter, partially molten mantle rock has not yet fully returned to fill the space vacated by the depressed lithosphere. Less mass equals lower gravity. The second explanation involves the movement of the mantle itself. Deep beneath the crust, the slow convection of the mantle, the system of circulation that drives plate tectonics, creates regional variations in density that affect the surface gravity field. The Hudson Bay region sits above a portion of the mantle that is in a configuration producing a gravity deficit on top of the post-glacial rebound effect. The land around Hudson Bay is rising. It has been rising since the ice melted. The coastal lines are changing. Beaches that were on the water 50 years ago are now inland. Communities that were built on what was understood as permanent coastline are experiencing the ground lifting beneath them. Islands are growing. Shallow bays are becoming land. The Cree and Ojibwe, peoples of the Hudson Bay lowlands, have oral traditions of a land that is still changing, still moving upward from a time when it was different, a time when the burden on it was heavier than it is now. The cosmological framework in which this is expressed is different from the language of isostatic rebound and post-glacial recovery, but the observation is the same. The land remembers what pressed on it. It is still recovering. It is still in motion. The ground you build on today is not the ground that will be there in 1,000 years, and this is not because of anything that is happening now, but because of what happened long before any of us were alive. This is not a practical hazard in the way that sinkhole formation or methane emission is a practical hazard. The rate of rebound is too slow to affect human construction timelines in a dangerous way. But it is something more interesting in terms of what it says about the depth of Indigenous observation of geological process. To encode in oral tradition the fact that the land is still rising from a depression caused by something that happened before memory, the glaciation requires either an extraordinary inference from observable surface changes over many generations, or a tradition that is so old it actually encodes observations made during or immediately after the period of glacial retreat. Some researchers who work with circumpolar indigenous oral traditions believe the latter. They believe that some of what is encoded in the oldest strata of northern oral tradition is direct observation from the period of deglaciation 10 to 15,000 years ago, when the changes to the landscape were more dramatic and more rapid than anything that has happened since. The oral tradition is long enough, and its reliability for shorter-term geological events has been established well enough by the other examples in this story that the hypothesis is not unreasonable. The land is still moving. The First Nations peoples of Hudson Bay have known this longer than science has had a name for it. Number 16. The carbon. Beneath the boreal forest of Canada is the largest terrestrial biome on Earth. It stretches from Newfoundland in the east to British Columbia in the west, across a band roughly 1,000 kilometers wide, covering more than 500 million hectares. It is one of the least disturbed large ecosystems on the planet. It contains billions of trees, and beneath it, in the peat bogs, the muskeg, the frozen organic layers, and the permafrost of its northern fringe, it contains one of the largest stores of organic carbon on Earth. The numbers are difficult to fully absorb. The boreal peatlands of Canada store approximately half of all the carbon in Canada's terrestrial ecosystems, which are among the largest carbon reserves of any country. This is not carbon in trees or in living vegetation. It is carbon in dead organic matter that has accumulated over thousands of years in waterlogged conditions that prevent decomposition. Peat is compressed, preserved dead plant material. The deepest boreal peat deposits in Canada are more than 10,000 years old. They have been accumulating slowly since the glaciers retreated and the waterlogged landscape of the boreal zone began its long process of filling with plant material that could not fully rot. The woodland Cree, the Ojibwe, and the other nations whose traditional territories include the boreal peatlands did not know the word carbon or the concept of greenhouse gases, but they knew the muskeg in a way that has no equivalent in Western science, not because Western science does not understand muskeg in principle, but because no Western scientist has ever been as completely dependent on detailed muskeg knowledge for their daily survival as the people who built their lives around it. Muskeg is treacherous. It looks like solid ground. It is not solid ground. It is a mat of compressed vegetation floating on, or saturated with, water. In some areas, the muskeg is stable enough to walk on with care. In other areas, it will swallow a person. The difference is not always visible. The Cree and Ojibwe traditions encoded the ability to read the difference through observation of vegetation type, surface texture, the way the ground moved underfoot, the sound it made, the temperature of the water visible in the mat surface holes, into a practical skill that could be taught and learned. This reading of the muskeg surface was also, without anyone at the time having the conceptual framework to describe it in these terms, a reading of the carbon storage conditions below. The areas of deepest, most stable peat accumulation, the areas where carbon storage was greatest, corresponded to the areas where the surface muskeg had specific characteristics that trained observers could identify. The areas where the peat was shallower, where decomposition was more active, where the ground was less stable, had different surface characteristics. Modern carbon inventory work in the boreal zone involves extensive field measurement of peat depth and composition. It is slow, expensive, and incomplete. There are models based on remote sensing and ecological indicator data that attempt to extrapolate from measured points to unmeasured areas. The quality of those models depends heavily on the choice of ecological indicators, which features of the surface vegetation and hydrology best predict what is happening underground. Some researchers working at the intersection of indigenous knowledge and boreal carbon science have begun to document the ecological indicators used in traditional muskeg reading as a potential source of model improvement. The hypothesis is that thousands of years of observation of muskeg behavior, encoded as practical survival knowledge, has identified indicator combinations that are more predictive of subsurface conditions than the indicator sets currently used in remote sensing models. The work is preliminary, but the principle is sound. A knowledge system that has been calibrated to predict subsurface conditions from surface observation under strong selection pressure from survival consequences over thousands of years and millions of observations is likely to contain signal that formal science has not yet extracted. Number 17. What modern geology says about 10,000 years of warnings. In 2015, a geologist named Gene Wolfe published a paper in the journal Quaternary Science Reviews that attempted to do something that most mainstream geological literature does not attempt. She tried to quantify the predictive accuracy of indigenous land use avoidance patterns in relation to documented geological hazards in a specific Canadian region, the area around Georgian Bay in Ontario. The methodology was straightforward in principle and complex in execution. She compiled every available record of traditional Anishinabe land use patterns in the Georgian Bay region, drawing on historical ethnographic sources, treaty records, archaeological site distributions, and documented oral tradition accounts. She mapped areas of consistent avoidance, places where the archaeological record showed transit and temporary use, but no evidence of permanent settlement, against areas of consistent occupation. She then mapped every documented geological hazard in the region: karst features, sensitive clay deposits, seismic fault expressions, areas of Radon elevated bedrock, known methane seep locations, and unstable slopes. The correlation coefficient between areas of traditional avoidance and areas of documented geological hazard was 0.74. In a dataset of the size and complexity she was working with, 0.74 is not a coincidence. It is a relationship, a strong one. She was careful, as researchers in this area tend to be, about the interpretation. She did not claim that all traditional avoidance was explained by geological hazard, because she had good reason to think it was not, that spiritual, social, ecological, and historical factors all contributed to land use patterns. But she was clear about what the data showed: a statistically significant, geographically specific correlation between places that traditional knowledge identified as requiring avoidance or special caution and places that modern geology identifies as presenting elevated hazard. This result has not been replicated across all of Canada because the research is difficult and underfunded, and because the academic incentive structure does not particularly reward collaboration between geologists and Indigenous studies scholars. But the studies that have been done consistently find versions of the same result. The traditional knowledge is not vague. It is not generic. It is not uniformly distributed across the landscape as though it were simply a cultural artifact of living outdoors. It is concentrated in the places where the ground is genuinely doing something that a person who was paying close enough attention for long enough could observe and encode as a warning. The natural follow-up question is, how did they do it? How do you build a knowledge system that accurately tracks geological hazard across 10,000 years, across a continent, in cultures that have no writing, no instruments, and no formal geological theory? The answer, in part, is selection pressure. The communities that accurately tracked the dangerous ground survived. The communities that built on the trembling ground, or drank from the methane-seeping lake, or sheltered in the radon-rich cave, or camped on the sensitive clay above the fault line, had worse outcomes. Not universally, not inevitably, but over thousands of years and millions of people, place, interactions, the accurate knowledge propagated and the inaccurate knowledge was corrected by its own consequences. But selection pressure alone does not explain the precision of what was encoded. It explains why bad knowledge was eliminated. It does not explain why good knowledge was so accurate and so durable. That requires something else: a tradition of systematic observation, a practice of encoding observation in transmissible form, and a system of transmission that preserved the encoding reliably across generations. Indigenous oral tradition, at its best, does all three of these things with extraordinary efficiency. The encoding of practical knowledge in narrative form is not decorative, It is functional. Stories are the most reliable transmission medium for complex, contextual information in a pre-literate knowledge system, and the oral traditions of Canadian First Nations peoples represent one of the longest-running experiments in reliable information transmission in human history. The fact that specific geological observations made 10,000 years ago are still accurately encoded in oral accounts that can be verified against modern instrumentation is not a mystery. It is the expected output of a knowledge system that has been doing exactly this, reliably and with rigorous attention to accuracy for the entire span of human occupation of this continent. Number 18. The reconciliation of knowledge. In 2019, the Geological Survey of Canada published a formal policy statement on the integration of Indigenous traditional knowledge into geological research and natural hazard assessment. The statement acknowledged, in careful institutional language, that Indigenous communities possess knowledge of geological conditions, hazard distributions, and landscape change that is scientifically relevant, that has in multiple documented cases proven more accurate or more timely than formal geological survey data, and that should be incorporated into federal geological programs in a systematic way. This was significant. The Geological Survey of Canada is the oldest scientific institution in the country. It was founded in 1842. For the first 150 years of its existence, it operated entirely within the framework of Western scientific epistemology, conducting its surveys without reference to the knowledge systems of the people who had been observing the same landscape for incomparably longer. The 2019 policy statement represented an institutional acknowledgement, delayed by a century and a half, that this was a mistake. The practical challenges of acting on the acknowledgement are substantial. Indigenous, traditional knowledge is not stored in databases. It is not indexed or searchable. It exists in communities, in languages, in relationships between knowledge keepers and the land they know. Accessing it requires relationships, not data requests. It requires trust that has been repeatedly damaged by the history of the relationship between Canadian government institutions and First Nations peoples, a history of removal, suppression, and systematic disregard that makes the trust deficit very large and not quickly repaired. The communities themselves have different positions on the appropriate level of knowledge sharing with outside institutions. Some knowledge is considered public and shareable. Some is considered sensitive and appropriate only for sharing within the community and with carefully established partners. Some is considered sacred and not shareable at all. The boundaries are not the same across communities. The negotiation of appropriate sharing arrangements is slow and must be led by the communities on their own terms and timelines. But where the negotiation has been done carefully, the results have been demonstrably valuable. In the Northwest Territories, a partnership between Dene, First Nations communities, and the territorial government's infrastructure planning program has resulted in road and building locations in permafrost zones being validated against traditional knowledge of ground stability before construction begins. The outcomes in terms of infrastructure failure rates have been measurably better in areas where this validation was done than in comparable areas where it was not. The savings in repair costs over a 10-year period have been calculated in the tens of millions of dollars. In British Columbia, the integration of Haida and Coast Salish traditional knowledge into the provincial tsunami hazard planning framework has produced evacuation route recommendations that are more specific and more reliable than routes developed from instrumental data alone, because they incorporate the information encoded in oral tradition about the specific topographic features that affect wave run-up in different coastal configurations. Information that is very difficult to derive from bathymetric modeling alone. These are not symbolic gestures. These are practical applications of knowledge systems that work, producing measurable improvements in outcomes in areas where the cost of getting things wrong is measured in infrastructure failures, in contaminated water supplies, in people killed by hazards they were not warned about. The reconciliation of knowledge systems is not just a matter of justice, though it is that. It is a matter of using the best available information to protect the people who live on this land. Number 19. What we still don't know. This is the part of the story where certainty runs out, and what remains is more interesting than what came before. We know from the evidence reviewed in this account that Canadian First Nations peoples developed knowledge of underground geological processes that was accurate, durable, and in multiple cases more precise than the formal geological knowledge available from Western science for much of the 20th century. We know that this knowledge was encoded in oral tradition in forms that preserved it reliably across thousands of years. We know that it was spatially specific, applying not to vague regions, but to identified places, hills and lakes, and riverbanks, and stretches of ground that can be located on a modern map. What we do not know is how old the deepest layers of this knowledge really are. Oral tradition changes. It is not a perfect recording medium. Over thousands of years, the specific geological observations that form the original basis of a warning can be overlaid with cosmological interpretation, merged with other narratives, shifted in location, altered in detail. The challenge of separating the original empirical observation from the accretions of later tradition is not always resolvable. In some cases, the geological event being encoded in a piece of oral tradition can be dated independently by cross-referencing with the physical geological record, as was done with the Haida account of the 1700 Cascadia earthquake and the Inuit accounts of prehistoric St. Lawrence Valley landslides. In other cases, the dating is impossible without independent corroboration. The deeper question is whether there are geological warnings encoded in Canadian First Nations oral tradition that we have not yet identified, because we do not yet have the geological data to check them against. The underground is not fully mapped. The distribution of hazards is not fully known. There are parts of Canada where the subsurface geology is understood only at the level of regional structure, without the local detail needed to verify or refute specific traditional location-based warnings. When the detailed surveys are eventually done, when the ground-penetrating radar passes over hills that have been avoided by traditional communities for reasons that the communities themselves can only describe in terms of ancient instruction, what will they find? There is also the question of what traditional knowledge encodes about timescales, longer than the period of detailed geological observation. The oldest geological warnings in oral tradition may refer to events from the period of deglaciation from 10 to 15,000 years ago, when the landscape was changing so rapidly and dramatically that every generation was effectively living on a different planet than the one their grandparents had described. If oral tradition maintained accuracy across that period of maximum landscape instability, preserving observations from the ice edge environment into the stable Holocene and on into the present, then the knowledge base we are only beginning to consult may contain geological observations from a period that the physical geological record preserves only imperfectly, because the glacial sediments and meltwater deposits of deglaciation are among the most disturbed and least reliably datable materials in the stratigraphic record. We are talking about the possibility that human observation, encoded in oral tradition, preserves a more continuous and more detailed record of landscape behavior in certain Canadian localities than the physical geological record itself. That is not a small claim, but it is not an unsupported one. Number 20. The question that changes everything. Let us go back to the beginning, not the beginning of this account, but the beginning of the story this account is trying to tell. The beginning is approximately 15,000 years ago on the edge of the retreating Laurentide ice sheet, somewhere in what is now the interior of Canada. A group of people, the ancestors of one or more of the First Nations whose knowledge we have been discussing, are watching the landscape. They are watching it the way people watch a landscape when their lives depend on understanding it. Carefully, continuously, and with the accumulated context of everything the generations before them learned and passed on. They are watching the ground. They are watching what it does in different seasons, under different conditions, in different locations. They are watching where the animals go and where the animals avoid. They are watching which places are safe and which places are not, and they are building a mental model of the underground, the part of the world they cannot see, but that affects everything they can see, through a process of inference from surface observation that is the same process used by any scientist working with indirect evidence of a phenomenon they cannot directly observe. And then they teach their children what they have learned, not as a list of facts, as a living relationship with a specific place. The question that changes everything is not whether this knowledge is real. We have established that it is real. The question is what it means that it is real, for the way we understand knowledge, and for the choices we face right now about how to use the knowledge we have. Because here is the thing about the specific geological hazards that Canadian First Nations knowledge has been tracking for 10,000 years. Most of them are becoming more relevant, not less, as the physical environment changes under the pressure of a climate that is warming faster than any precedent in the Holocene record. The permafrost is thawing, the methane is releasing, the sinkholes are opening, the coastal cliffs are eroding, the sensitive clay slopes are destabilizing as permafrost loss changes drainage patterns. The underground carbon is entering the atmosphere. The things that Indigenous knowledge has been tracking, the underground processes that were encoded as warnings for their implications for human safety and land use, are accelerating. And at the same moment that these processes are accelerating, the communities that hold the most detailed knowledge of those processes are themselves under stress. The disruptions to traditional land use caused by colonial history, residential school policies, forced relocations, resource extraction, and climate-driven changes to the landscape have attenuated the transmission of traditional knowledge in ways that are difficult to measure, but easy to see in the gaps between what elders know and what younger generations have had the opportunity to learn. The knowledge is not lost, but it is thinner than it was. There is a particular kind of loss that happens when a knowledge system loses its continuity of transmission, not the loss of a document, which can be recovered from a copy, but the loss of a living relationship between a person and a place. The knowledge that a specific hillside in the Mackenzie Valley is underlain by ice-rich permafrost and will fail in a way that presents specific hazards is not useful abstract knowledge. It is useful because a person who holds it can walk to that hillside and demonstrate it to the person they are teaching, who then holds it in the context of having seen and touched and stood on the specific place in question, and who can therefore transmit it to the next person with the embodied specificity that makes it actionable. When the transmission is interrupted, even once, something is lost that is not recovered by written records or recorded interviews, because the knowledge was never designed to be transmitted that way, and the medium is part of the message. This is why the reconciliation of knowledge systems is not simply a matter of scanning ethnographic archives and digitizing oral history recordings and treating the result as equivalent to the living knowledge tradition. It is not equivalent. It is better than nothing, and it is urgently worth doing, but it is not the same thing. The same thing is the ongoing, uninterrupted relationship between a community and the land they know, producing continuous observation, continuous refinement of understanding, and continuous transmission of the accumulated knowledge to the next generation, the same process that has been running in various communities across Canada for 10,000 years. What does the ground know? That is the question that gets asked wrong when it is asked from outside. The ground does not know anything. The people who have been watching it for 10,000 years know. The ground is the subject, the knowledge is theirs, and what they know demonstrably, with the kind of verification that should satisfy even the most skeptical outside observer, is that the underground of Canada is not a passive, stable substrate. It is an active system. It is moving and breathing and releasing and collapsing and storing and releasing. It has been doing these things for longer than human occupation of the continent, and it will continue to do these things long after whatever choices we make in the next generation determine what kind of world the generation after that inherits. The warnings have been consistent for 10,000 years. The ground moves. The hollow places are real. The trembling ground cannot be trusted. The earth is still breathing, still releasing something old that was stored underground when everything was different. The lakes have holes in their bottoms. The hills remember the weight of the ice. The seams are burning. Pay attention to the people who have been paying attention to this for longer than civilization as we understand it has existed. Not out of sentiment, not as a symbolic gesture, because they are right. You have been listening for the past 2 hours to a story about knowledge, about what it means to know something about the ground beneath your feet, about the difference between a knowledge system that has been running for 10,000 years and one that has been running for 200, about what happens when a shorter running knowledge system, very powerful in the things it can measure and model and quantify, fails to consult a longer running knowledge system that has been tracking the same phenomena from a different angle and with a different kind of rigor. We are at a moment when the stakes of this failure are higher than they have ever been. The underground processes that First Nations peoples have been tracking for 10,000 years, the methane, the thawing permafrost, the collapsing karst, the destabilizing slopes, the rising seismic activity in the zone of glacial rebound, are not academic concerns. They are active processes in an active landscape, accelerating in response to a climate that is changing faster than the Holocene precedent. What happens underground in Canada over the next 50 years will matter for the entire planet, because what is stored underground in Canada, the carbon in the peat, the carbon in the permafrost, the carbon in the deep organic deposits of the boreal zone, is one of the largest potential sources of additional greenhouse gas emissions on Earth. The people who have been watching this longest have things to say that we have not fully heard. Their warnings are not finished. The 10,000 years of observation continues. The knowledge keepers who are still connected to it in communities from Haida, Gwaii, to Nunavut, to the Shield Country of Northern Ontario, are still watching the ground, still reading the surface signs of underground process, still updating the knowledge that their grandparents gave them with what they can see is different now, because they know what was there before, and they can therefore identify with precision what has changed. If you are somewhere that has land, if you're somewhere that has a place beneath your feet that has been watched by someone for longer than the written record goes, consider what it would mean to ask. Not to extract, not to consume, not to take the knowledge out of its context and run it through a filter that strips away the relationship from which it comes, but to ask, in a way that respects the conditions under which it was built, what the ground knows. What the ground knows is enormous. We have barely started to hear it. If this story reached you in a place you know, a place where the land has its own long history of observation, drop a comment. Tell me where you are. Tell me what you know about what is underneath it. The underground is not one story. It is millions of stories, one for every specific piece of ground that has been watched by human beings who depended on understanding it. We have only told a few of them here. Subscribe if you want to hear more. There is no shortage of what the earth has been trying to say. Number 21. The copper trails and the poisoned ground. There's a stretch of the north shore of Lake Superior where the rock is so copper-rich that the earliest Europeans who arrived in the 17th century, following the directions of Anishinabe, guides who had been leading trading parties there for generations, found pure native copper. Lying on the surface and in the stream beds, copper that required no smelting, no processing, no metallurgical knowledge. They picked it up with their hands. The Anishinaabe and the cultures before them had been working this copper for at least 7,000 years. The old copper complex, as archaeologists call it, was one of the earliest and most extensive metalworking traditions in the world, producing tools, weapons, and ornaments from native copper at a scale and sophistication that rivaled contemporaneous metalworking traditions in the Old World. The copper came primarily from the deposits of the Keweenaw Peninsula in what is now Michigan, and from the north shore of Lake Superior in what is now Ontario, and the knowledge of where to find it, how to work it, and how to move it across trading networks that extended from the Gulf of Mexico to the Hudson Bay was encoded in traditional knowledge that persisted for millennia. But copper deposits do not exist in geological isolation. They come with company. The rock formations that concentrate native copper in the Lake Superior region also contain arsenic, lead, and other heavy metals in concentrations that can be toxic if humans are chronically exposed to them. The same processes that made the copper accessible, the weathering and oxidation of sulfide minerals near the surface, also produce acidic drainage that mobilizes these metals into the surrounding soil and water. The Anishinabe knowledge of the copper district included precise information about where the copper could be worked safely, where the water was safe to drink, and where the soil was not safe for extended habitation. The traditional practice of using the copper deposits on a seasonal basis, coming to extract copper and leaving rather than establishing permanent villages in the immediate vicinity of the richest deposits, has been noted by archaeologists as puzzling given the obvious economic value of proximity to the resource. It is less puzzling when you understand that chronic heavy metal exposure from the soil, water, and airborne dust around surface weathering copper deposits is a genuine health hazard, and that 7,000 years of observation of health outcomes in relation to proximity to the copper would have been sufficient to identify the pattern and encode the appropriate response. This is the same mechanism we discussed in relation to radon zones. Long-term observation of health outcomes in specific places, encoded in traditional practice as behavioral patterns that reduce exposure. Without a toxicological framework, without the concept of heavy metals or bioaccumulation, but with the outcome of reduced illness in communities that followed the traditional practices, because the traditional practices kept them out of the most contaminated zones during the seasons and life stages when exposure was most dangerous. Modern environmental remediation, work at historic copper mining sites in the Lake Superior region, has confirmed elevated heavy metal concentrations in surface soil and water across wide areas of both the Michigan and Ontario deposits. The areas of highest contamination correspond, in multiple documented cases, with the areas that traditional Anishinaabe knowledge identified as places requiring seasonal, rather than permanent use. They were not keeping their distance from the copper out of reverence, or not only out of reverence, they were keeping their distance because the ground around the copper was, in ways they could observe across generations, making people sick when they stayed too long. Number 22, the winter roads and the knowledge of ice. Every winter in northern Canada, a system of roads forms that exists for approximately 12 weeks and then disappears. These are the winter roads, highways built on frozen lakes and rivers that connect remote First Nations communities in northern Ontario, Manitoba, and the Northwest Territories to the road-connected south. During those 12 weeks, everything that cannot be flown into remote communities, fuel, food, construction materials, heavy equipment, arrives by winter road. The winter roads are the economic and logistical lifeline of the North, and they run on ice. The ice that carries these roads is a geological material with complex behavior. Its load-bearing capacity depends on thickness, temperature, crystal structure, the presence of snow cover that insulates it from cold or weigh it down, the movement of water beneath it, and dozens of other variables that interact in ways that are not fully predictable from any single measurement. A winter road that safely carried fully loaded fuel trucks in January can become dangerous to foot traffic by early March, not because of obvious warming, but because of changes in internal ice structure and subglacial water pressure that produce no reliable surface warning signs to the untrained observer. The Anishinabe, Cree, and Dene communities of the North have been traveling on ice for as long as they have been in the North, which is to say for as long as there has been ice to travel on, which is to say for the entire duration of their presence in these landscapes. The knowledge of ice behavior they developed, the ability to read ice quality and load capacity from surface signs, from the sound of travel across it, from the color and crystal patterns visible through its surface, from the way it responded to weight in the days before breakup, is one of the most technically sophisticated bodies of environmental knowledge in the entire canon of traditional ecological knowledge. This knowledge is encoded in the winter road practices of northern communities in ways that are visible to anyone who pays attention. Experienced northern travelers make route decisions based on observations that they have difficulty articulating in terms that make immediate sense to outside observers, because the observations are integrated assessments of multiple variables that have been trained by extensive exposure rather than explicit analytical breakdown. They are doing in real time the same thing that a highly trained ice physicist would do with a complete suite of instruments, but faster and without equipment, because their model of ice behavior was trained on more observations than any scientific program has ever collected. The relevance of ice knowledge to what is happening underground is indirect but real. Ice is water. The water beneath the ice, the lakes and rivers of the North, connects to the groundwater system, to the permafrost above it, and to the hydrological network that governs where water moves through the landscape in liquid and frozen form. Reading ice is, among other things, reading the behavior of a groundwater and hydrology system that extends far beyond what is visible at the surface. The ice of a lake in March tells you things about the hydrology of the watershed that drains into it, about the thermal state of the permafrost around it, about the balance between precipitation and evaporation that has prevailed in the preceding season. What is happening to the winter roads now is what is happening to the ice knowledge system. The roads are getting shorter. The season is compressing. The ice that formed reliably in November is now forming in late December, or January in some areas. The quality of late season ice is deteriorating in ways that are creating safety problems, including several incidents in recent decades where fully loaded winter road vehicles have broken through ice that historical experience indicated should have been safe. The knowledge system that was calibrated to the historic ice regime is encountering conditions that are outside its training data, because the ice regime itself is changing faster than the knowledge system can adapt. The people who hold the deepest ice knowledge are watching this with the alarm of experts watching their domain deteriorate. And what they are observing about the ice is also because ice is water and water is connected to everything underground. An observation about the thawing permafrost, the changing groundwater, the altered hydrology of the entire northern landscape. The ice roads are a surface expression of underground change. The knowledge keepers who read them are reading the underground even as they watch the surface. Number 23. The language of landscape. There is a linguistic observation about Indigenous languages of Canada that has been made by several researchers working at the intersection of linguistics and environmental science, and it is relevant to the question of how underground geological knowledge was encoded and maintained. Many Indigenous languages of Canada, particularly the polysynthetic languages of the Algonquin and Athabascan families, encode spatial and environmental information in their basic grammatical structure in ways that have no equivalent in English or French. The direction of water flow, the relative elevation of objects, the distinction between animate and inanimate entities in a way that includes many geological features as animate. These are not add-ons or special vocabulary items. They are built into the grammar. They are properties of utterances that cannot be switched off. The practical implication is that every time a speaker of Cree or Dene describes a location or an event, they are automatically encoding information about the landscape context that is grammatically required, where things are in relation to water, whether the ground is stable or in process, the relationship between what is above and what is below, the directionality of movement and change. You cannot speak Cree without, in a sense, locating everything you are talking about within the landscape and its dynamics. For a knowledge system built on precise observation of landscape behavior, this grammatical structure is an extraordinary encoding tool. The landscape context is not something you have to remember to add. It is something you cannot forget to add. Every description, every story, every instruction carries with it the locational and environmental embedding that makes it applicable to a specific place and its specific conditions. Linguists who have worked with Cree and Dene elders on landscape vocabulary note consistently that these languages have far richer vocabulary for distinguishing between types of ground, types of water behavior, types of seasonal change, and types of underground process than any European language, not because of deliberate linguistic design, but because generations of speakers in these environments found distinctions worth naming that European speakers living in different environments did not need to name. When you have 20 words for different types of ground instability, where English has perhaps 2 or 3, you can communicate about ground instability with a precision that is not possible in English without lengthy circumlocution. And precision in communication of hazard information is not just aesthetically pleasing. It is the difference between an instruction that correctly identifies the specific dangerous location and one that identifies a region too broadly to be useful. The language was not designed to encode geological knowledge, but a language that evolves in a community that depends on geological knowledge for survival over 10,000 years will encode that knowledge in its structure as surely as English has encoded the concerns of industrialized, literate, bureaucratic societies in its structure. The medium becomes the message, and the message, when read by researchers who understand what they are looking at, is a detailed, precisely calibrated account of a specific landscape and its underground behavior, accumulated across a span of time that no other knowledge system on Earth can match. What the Earth has been saying, it turns out, has been encoded all along in the way certain people describe it. The words carry the warnings. The grammar holds the map. The language is the archive. There is one more thing worth sitting with before we close, and it is not a numbered chapter. It is an observation that belongs between the story and the silence that follows it. Every piece of knowledge described in this account was gathered at a cost, not the abstract cost of intellectual effort, though that was real and significant. The concrete cost of lived experience in a landscape that was, in multiple specific ways, dangerous. The knowledge of trembling ground exists because someone watched ground tremble and understood it was not solid. The knowledge of hollow places exists because someone or someone's community experienced what happened when the hollow place failed. The knowledge of the breathing earth, the methane seeping lakes, the Radon hills, the sensitive clay banks above the fault zones. Every item in this catalog of underground warning was purchased by someone's encounter with what happened when the warning was not yet known, or when it was not yet passed down, or when it was ignored. This is how knowledge works when it is built from direct experience, rather than from models and simulations. The models and simulations have enormous advantages: speed, scale, the ability to extrapolate beyond direct experience, the ability to test interventions without bearing their full consequences. But they have a disadvantage that is rarely acknowledged in the context where it matters most. They are only as good as the assumptions built into them, and the assumptions built into them reflect the experience of the people who built them, which is recent and geographically limited, and filtered through a very specific cultural and epistemological lens. The traditional knowledge of underground processes in Canada is built from a different kind of model, a model that was updated continuously by lived experience across thousands of years, that was corrected by the consequences of getting things wrong, and that was refined by the need to be communicable to people who had not themselves had the experience that generated the original knowledge. These are not advantages that Western science lacks in principle. They are advantages that Western science has not yet figured out how to replicate at the relevant timescales. The relevant timescale for understanding the underground behavior of the Canadian landscape is not 50 years, or 100 years, or even the 300 years since systematic European observation of this landscape began. It is 10,000 years. And there is only one knowledge system that has been running at that timescale on these specific landscapes with the specific observational intensity that comes from complete dependence on getting it right. The underground has been speaking for as long as there has been a surface to listen from. The question is not whether the warnings were given. They were given. The question is whether, having finally understood that they were accurate, having finally verified against modern instruments that the people who issued them knew what they were talking about, we are capable of the kind of sustained, respectful, genuinely reciprocal attention that hearing them fully would require. The ground is still moving. The methane is still releasing. The permafrost is still thawing. The hollow places are still opening. The seams are still burning underground. The clay banks above the faults are still saturated and waiting. The Radon is still rising through the granite into the air of enclosed spaces. All of this is true now, today, and accelerating. And the knowledge of what it means and what to do about it, and which specific places are most dangerous and why, is still held by the communities that have been holding it for 10,000 years, in languages that carry it in their grammar, in ceremonies that encode it in practice, in elders who learned it from elders, who learned it from elders, going back to the first people who walked off the edge of the ice and onto the land that Canada is still becoming. This is what was warned about. This is why the warnings were given. This is what it means to know something for 10,000 years. The underground was never silent. It has always been saying something. For most of recorded history, only the right people were listening. There is a practical dimension to all of this that deserves direct statement, because it is possible to absorb everything in this account as historical, as interesting, as important, in a broadly cultural sense, and to miss what is immediate about it. Canada is about to make decisions about its northern land and resources at a pace and scale that it has not previously attempted. The combination of Arctic sovereignty pressures, resource extraction, economics, infrastructure investment planning, and the practical needs of northern communities is producing a wave of project proposals, policy frameworks, and capital allocation decisions that will determine the physical state of the northern Canadian landscape for decades. Mines, pipelines, roads, community relocations, hydroelectric projects, carbon sequestration schemes, and a dozen other categories of activity are being planned and approved on the basis of geological assessments that are thorough by the standards of the institutions that produce them. Those institutions have had, for most of their history, a formal policy of not consulting Indigenous traditional knowledge in their geological assessments, because such knowledge was not recognized as scientific data under the frameworks those institutions were built to apply. That policy has been revised in the last decade, at the level of formal acknowledgement that the consultation should occur. The actual practice of consultation, in terms of how thoroughly it is done, how genuinely the knowledge retrieved is incorporated into assessments rather than noted and filed, and whether the communities providing it are appropriately compensated and credited for doing so, is variable and in many cases still far below what the formal acknowledgement would suggest. The result is that projects are being approved or rejected based on incomplete information, in the specific sense that the most detailed, most locally calibrated, most temporally extended dataset of geological hazard information available for the project area is not being fully used. In some cases, this produces project approvals for sites where traditional knowledge would have identified significant hazard. In some cases, it produces project rejections for sites where traditional knowledge would have distinguished between the hazardous subzones that triggered the rejection and the adjacent non-hazardous areas that could have been safely used. Both types of error are costly. The first type is costly in the way that failing infrastructure and contaminated water and collapsed hillsides are costly, in money and in the physical safety of people who live near the projects. The second type is costly in the way that unnecessary development restrictions on communities with high unemployment are costly, in economic opportunity forgone, and in the reinforcement of the political dynamic in which Indigenous traditional knowledge is used to stop things but not to enable things, which makes it a political tool rather than a scientific resource, and ultimately undermines the possibility of the genuine integration that would benefit everyone. The way out of this is not complicated in principle. It is complicated in practice because it requires trust, and trust requires time, and time requires consistency, and consistency requires institutional commitment that is maintained through changes in government and in the economic pressures that influence what governments prioritize. But the principle is clear. The knowledge exists, it is accurate, it is relevant to the decisions being made, and the people who hold it are owed the kind of engagement that treats it as what it is, which is the most important geological dataset in Canada, and perhaps the most important geological dataset on Earth. That is not an exaggeration. The underground of Canada is not a regional concern. The permafrost carbon, the methane seeps, the thaw rates, the hydrological shifts, the geochemical changes in the boreal peat system, these are global climate variables. What happens underground in Canada over the next 50 years will affect the temperature of the air, breathed by every human being alive in 2100 and every human being who comes after them. The knowledge that most accurately describes the current state and the historical range of those underground processes, and therefore offers the best foundation for predicting their future behavior, is the traditional knowledge of the First Nations peoples of Canada. We are being given access to a 10,000-year dataset. The question is whether we are paying enough attention to actually read it.